Let's look at this. What is this? It's a vehicle aero map, and the reason I'm showing this is just what I've been describing before. That it's not just one condition, that one straight line condition in CFD that you're looking at. You've got to look at so many other conditions where it's actually more important to have aero downforce than in a straight line condition. And as an example, this is just a speed trace. So the orange one is a speed trace of the car. You can see the corners almost. So some of you can probably pick that up straight away. Um, these two, I believe, are ride height. I've lost the legend here somehow. So what this is saying is we have such good vehicle data acquisition systems on the race cars now that they measure and send back lots of data for the engineers to track during the operation of race car. So you can measure front and rear ride height, roll, steer. You can even measure airflow data. So you have velocity. You normally have um, a pitot-static tube in the front of the car. You would have noticed on most of the race cars, all the race cars will have one. You can measure velocity. It's also normally a yaw probe, so it'll measure the yaw angle as the car goes around the track as well. Um, they can then be filtered down uh, into some sort of operational envelopes. And I'll tell you what I mean in the next slide. And what you could do is you can take all of this data as the car goes around one lap, and then you could filter that down into these different bins almost. So it's a straight line conditions. Within this, obviously, you'll have different straight line conditions. You can have the car at a slightly higher ride height or a lower ride height, depending on how fast it's going down different straights of different tracks, uh, braking conditions, acceleration, and cornering. But within these sort of high level bins, you can put all of this data into that. This is a bit more of a different way of looking at it. The same thing that I just described. If you have a plot of front ride height versus rear ride height, and you look at where these bins lie, so an acceleration zone might be here. So you'll have lots of data points that lie here, but it can also it'll normally be higher front ride height and lower rear ride height. So it can go down here as well. A straight line, you're sitting mostly around here because you've got lots of load on the car, so it's squatting quite a lot. High speed corners, you're sort of sitting around here. Generally low front and rear ride height. Braking can be quite a big zone depending on uh, what which part of the track you're braking. You could be braking from a corner, from a straight, or things like that. And then low speed corner generally sits up here. Your ride heights are quite high as you're trying to negotiate a, a very low speed corner like in Monaco or well, most corners in Monaco. But this is a very sort of, it just gives you an idea that the data that comes from a racetrack can be put into these zones, and this is important because this is where your CFD simulations sit. So if you specify that I want to look at high speed corner, then you're going to be looking at some of these points, some of these ride heights from here. So a front ride height of some value, say 15 or 20, and rear ride height of 60 or 70 or something like that. So for a high speed corner, so that definition generally comes from the racetrack. Um, it tells you where the envelope of the car of where it can sit. At the dynamic ride height of the car, that can be calculated from the static weight aero loads on the axles, and you can actually calculate how much the wheel is moving, because you have the spring stiffness and you have the stiffness of the tire itself. So you can add those two. So you've got your spring and tire K, and you can calculate the movement in the in the wheel and suspension. And this is actually quite used. Well, this is the most important thing to define your ride height as well as the contact patch setup. And we look at this in a case study. That'll be quite interesting. Then let's move to. We're still sort of thinking about various things around setting up a simulation, and then we'll start looking at the surface meshing and all that stuff. So while we're thinking about this, what happens when we change ride height? So let's say you set up a certain simulation as a baseline. Uh, how do we then change it? So a lot general practice is to um, achieve different ride height configurations by moving the external domain while the car remains flat. And what are the reasons that we do this? Because it makes comparison between different runs quite convenient because the car is in the same place. So you just move the domain like you can see in the red box here to change your rear ride height and the front ride height. And you can you're looking at it only in 2 dimensions. So you're also changing the roll and all of as well. It's also very efficient for exporting CFD results into CAD or sharing Aero improvements with CAD designers. So imagine if your car was all over the place, is moving different pitching in different simulations, and you wanted to show some streamlines to a surfacer or a CAD designer. You'd have to then reposition your streamlines into the base car model, which is not very efficient. So it's easier if it's the car stays in a design condition from the CAD package, and then you're moving your domain to achieve the different ride heights and roll and steer.